But now I'd like to introduce Professor Ian Moore. He's from Queen's University in Canada, and he's going to be talking to us today about the advancing designs of liners for gravity, sewers and culverts, and also for water pipelines. There's been design methods that have been developed for spray liners on corrugated steel and concrete culverts and sewers, and we'll be discussing some of that and the new methods that have also been developed to estimate stress and strain in CIPP liners, particularly looking at spanning across joints and ring fractures in rigid and sewer pipelines. So without further ado, I will pass over to Ian. Thank you, Ian.
Thanks very much, Sandra, and thanks for hosting this visit. And just a quick thank you for Sean Greenwood, who helped set up this seminar, and also for Catherine and Zara, who are supporting this from the Pipeline Guild. So it's really nice to be talking to you again. I had a lovely visit to one of your big meetings in London a few years ago. And since I'm back in your beautiful country, England, for a couple of weeks, I thought I'd reach out to Sandra and offer to provide some of my, or a discussion of some of my recent research. And yes, I'm going to be talking a little bit about some work I've done on cured in place pipeliners and sprayed liner design. So on the cured in place pipeliners, one of the things that we need to think about for some liner projects is the impact of ground deformations on the performance of those liners. And I've had some projects in the last 10 years looking at protecting existing pipe systems, in particular cast iron water pipes and concrete sewer pipes and clay sewer pipes, from ground deformations associated with tunnelling. And as a result of those consulting projects, I've been doing some research to determine or develop some design equations that allow us to estimate what sort of stresses and strains we'll get in the liner, where they're spanning across joints in those rigid pipes, and where they're also where we might have a new ring fracture developing as a result of longitudinal bending, say in a cast iron water pipe. I've also had some projects in the last few years for industry. In particular, there's a tollway across the Greater Toronto area, the 407 ETR, where they're looking for the use of sprayed liners to rehabilitate both corrugated steel pipes for that tollway, but also for the City of Toronto. They're very interested in using these sprayed cementitious liners for deteriorated reinforced concrete pipes. So I'm going to just give you a little summary of the research that I've done in that area. What I'm going to try to do this afternoon is focus on the practical outcomes. So I won't be talking about deriving equations and a lot about the testing and so on. It's more an opportunity just to introduce some of the publications which present the design equations that are now available for doing these sorts of, or tackling these sorts of projects. So this picture on the top right-hand part of the screen shows an experiment that we performed a few years ago in the lab at Queen's, looking at a cured in place pipe liner installed within a pressure pipe, in this case, a steel pressure pipe, which really was as a sort of a surrogate for a cast iron pipe. So it's a lot easier to deal with a steel pipe in the lab and in buying one off the shelf and so on. And what we're interested in, can you see I'm hoping you can see my mouse. Sandra, I don't know if your mic's on. Can you see the mouse?
Yes, we can. Thank you.
Very good. Thanks, mate. So where that crack or that joint is opening at the bottom here, as a rotation is imposed across this joint or this fracture, we will get stretching of the liner at this location. And so some of the questions that we've been working to address is, can liners be designed to withstand those ground motions? How are stress and strain in the liner related to the rotation of the joint and the extension, the axial extension that you can develop at that joint? How does internal water pressure affect the liner stress and strain? And is the friction coefficient between the liner and the host pipe controlling the response? And also, one thing we may be interested in is understanding how far away from that joint does slip develop between the liner and the host pipe. And that can be relevant. For example, if we've got a cast iron water pipe with a liner, we have to think about the service connections that are attached to that pipe system. And one concern is, will that slip that's developing interrupt flow or cause damage or leakage at service connections? So understanding how far away that slip develops under certain circumstances can help us judge whether or not those service connections are going to be compromised by those ground movements. So in the slides that follow, I'll be actually showing the citation of papers that we've either published or in this case is currently under review for specific journals. This work that I've done, or some of this work that I've done on liners, CIPP liners, is from a former student, Kiji Chai. And so this is one of the papers that we've produced that's currently under review. And basically what he did was he looked at this scenario here. In this case, we're seeing that the joint opening is at the top of the pipe. We're looking at a rotation on either side of that of phi, or if you like, a total joint rotation of 2 phi. And this first set of results shows us what is the stress, the local stress, axial stress that develops, normalized by that rotation angle in radians. For this particular liner system, here's the modulus of the liner and some of the characteristics of this particular case that we've studied, and the way that stress varies away from that joint. And the stress for the linear theory that we've used in these first studies of this phenomenon, we're assuming that the rotations are small. We're looking at stresses before yield because we want to design these liners so that they do not yield. Certainly the long-term performance would be compromised likely if those liners were yielded as a result of the ground deformations. So we've got some calculations of how those stresses vary along, and also there's some results here on the inside and outside of that joint. PG performed a parametric study where he looked at a range of different pipe geometries, a range of diameters, a range of liner thicknesses, T subscript L, a range of friction coefficients, mu, between the liner and the host pipe, a range of liner moduli, and then this rotation half angle phi. And this is essentially a curve fit to those finite element results. And so we've now got an equation that allows us to estimate what is that longitudinal bending stress that we will develop in this gravity flow liner, or this liner in a gravity flow pipe, based on these parameters. We can do a little study to see how does that longitudinal stress, that longitudinal tension, normalized by the angle of rotation and the modulus of the liner, how does it vary as a function of friction coefficient, mu? How does it vary as a function of the thickness to diameter ratio of the liner? And what we can see is that, in fact, it's not very sensitive to those parameters. So that ratio starts at about 0.33. It rises up to about 0.55. So actually, we can get pretty reasonable design estimates just as calculating that maximum tensile stress. It's just going to be about 0.5 times the rotation half angle in radians times the modulus of the liner. And this might be up to about 25% conservative for friction coefficients over about 0.1. But instead of being anxious or having to figure out what might that friction coefficient, what might it be, we can just take a conservative estimate of that friction coefficient and get a decent design estimate for our assessments. Now, the next solution I wanted to talk about, and the next set of results, relates to pressure pipe liners. And when we have pressure pipe liners and we impose some sort of opening of the joint, and I can see that this picture is actually a little bit, there's a problem with it. We can't see the liner. There's supposed to be a liner in here, but it's gone invisible, unfortunately. Something about my drawing has left something to be desired. But imagine that there's a liner inside here under the action of internal pressure that's holding that liner in contact with the host pipe, and we're imposing this axial extension. And it's in fact possible to develop a closed form solution. And again, here is the citation to that publication, which is in Computers and Geotechnics. And what we find is that the maximum strain we'll get in the pressure pipe liner is equal to the opening distance, UA, that's the amount by which this liner or this joint or this crack opens under the ground motion, the internal pressure that's applied in this water pipe, again, the friction coefficient between the liner and the host pipe, and then the modulus of the liner and the thickness of the liner. So it's a function of the square root of those properties. We can also find the maximum tensile stress if you prefer to do design based on stress. And also, here is the solution for the slip length. So this tells us how far away from this joint or this crack that's opening does slip develop between the liner, and we mobilize the shear strength and that movement. So how far away would the service connections have to be in order to have them not compromised by this type of motion? And so this is again quite useful. It's like little equations that we can put into a spreadsheet, and we can do some calculations. We can look at some typical values here for what might be a plausible set of parameters. So here I'm plotting strain on the vertical axis. I'm plotting gap width. So how much does that gap open in millimeters? And typically we'd think of that gap opening by maybe 1 to 5 millimeters in a typical set of ground motions. And then here the solution has been normalized by the modulus and the thickness of the liner divided by the pressure and the friction coefficient. And here are some different values which cover a range of typical liner types and also pressure and friction coefficient ratios. So for example, if we had a liner modulus, this might be a modulus that we could have for a typical, say, an epoxy resin liner, and it might be reasonable for a polyester liner as well. Let's say a typical water pressure system in Canada would be running at about 500 kilopascals. It's about 70 psi, depending on which units you're using here in England. And a typical friction angle here, the calculations assuming 10 degrees of friction angle between the two systems. And these 3 points tell us about what sort of behavior we would get, or what sort of stresses and strains we get, depending on 3 different thicknesses of liner, say a 12.5 millimeter liner, a 5 millimeter liner, and a 2 millimeter liner. So it gives us an idea as to what sort of strain values we might achieve, and how we can control that strain level by specifying liners of different thickness. Now, a typical epoxy resin liner might have a strain capacity of between 0.8 or 0.7 and 1%, maybe even a little bit higher. And so we might think in terms of a limiting strain up in this region here, and we can use these equations to figure out what sort of liner we might specify in order to survive those sorts of ground motions. Here, it's giving us an idea of the slip lengths, so the distance from that joint or fracture and how far away slip will develop. So we're looking at again, these sorts of ranges of parameters and sort of gap widths here. And let's say, for example, we've got a 5 millimeter thickness liner, which is opening by 2 millimeters. We would have slip about 0.5 meter away. Whoops, I'll just go backwards because I hadn't finished there. Slip about 0.5 meter away. Whereas if we went to a different sort of liner, we might have slip going up to 1 meter or so away. And so these are distances that aren't particularly intimidating depending on how long your pipe segments are, and they allow us to assess whether those service connections might be compromised. Now, we did some computer analysis, and I'd just like to acknowledge the contribution of Michael Brown to this little bit of work. And we looked at, well, what would happen if we were to, let's say we had a tunneling project where we went in and we supported the cast iron water pipes prior to the tunneling exercise, so prior to the imposition of these ground motions, and we allowed the gap to develop, let's say at an internal pressure of 420 kilopascals. And this is for this particular analysis we've done here. And we would get, as the gap opened, let's say the gap was expected to open 5 millimeters under this sort of stretching. Then we would get a axial stress developing of about 18 megapascals, which is quite a high value, and it would be up close to the yield limit of a typical epoxy or polyester liner. But what we've done here, we've said, okay, what happens is temporarily, if the water authority was to reduce the pressure in that pipe, and by reducing the pressure, let's say for a 30-minute period, for a 1-hour period, so we need to do that for a limited period of time, because of course reduced pressure will have issues in terms of firefighting and having the ability to produce water from a hydrant in case of a fire event. But just temporarily we can lower the pressure, and what this allows to happen is slip then to develop between the liner and the host pipe. That slip will extend much further from that joint or from that fracture. It will allow the joint to stretch over a much longer distance, and therefore the stress will reduce as a result. And we can see here is that as the water pressure is decreasing, there's a steady decrease in the maximum axial stress as we get some sort of elastic recovery as that slip occurs away from the joint. And so what this tells us is that we can manage those stresses with some sort of temporary reduction in pressure, and then let's say we go back down to 100 kilopascals. We can then repressurize the system back to, say, the 420 kilopascals, and we'll only partially recover axial stress. So it's a convenient way that we can consider of managing that tensile stress in the liner, which will allow it to then last a lot longer during a sort of a long-term service life. Now, we don't have a closed form solution for pressure pipe liners under rotation, but what Keiju did was he looked at rotation with finite element analysis, and what we found is, in fact, the closed form solution I just presented actually works very well. If you think of this maximum gap up here at the top of the section of the joint that's rotating, if it's opening by this distance UA, we can calculate that gap here is just going to be the diameter times twice this or times this rotation angle, which is 2 times phi in radians. And actually, the closed form solution provides very good estimates of axial stress and strain. So we can use that same closed form solution for axial extension for this rotation case, but also for combinations of rotation and axial extension. Okay, so that's the first half of my presentation. Now I wanted to move on to cementitious sprays. And some of the questions that I've been asked by industry is, how do we do structural design of these sprayed liners? These are sprayed cementitious liners, typically involving Portland cement, but also something like maybe some geopolymer material. That's like rock fibers, which people use in these liners. Can we develop a design theory, a structural design theory? Can we use rigid pipe design theory to control cracking so that we can select the liner thickness to prevent cracking? How are moment demands affected by the host pipe and liner thickness? So the soil pipe interaction is going to be influenced by the stiffness of the host pipe, but also the stiffness of the liner, which is a function of the thickness of the liner. Another question is, do we get composite action between that sprayed liner and the original, let's say it's a corrugated steel host pipe? More questions relate to the use of these sprayed liners in reinforced concrete structures. And what is the effect of the condition of the host pipe, that old concrete pipe that we're repairing? How does that host pipe condition influence the required thickness? We may have a situation where the joints are leaking so that the barrels of the host pipe are intact, and we're just providing the spray to stop those joint leaks. So what sort of thickness is needed in that circumstance where we're not trying to reinforce the barrel strength? We're just trying to seal the leaking joints. What happens if we've got the normal condition with reinforced concrete, where we expect cracking in the reinforced concrete past the tension steel under normal service loads, right? We design reinforced concrete structures to crack, and we try and control the widths of those cracks. So if we've got that normal surface condition, what sort of thickness of liner might we need? Alternatively, we might have a situation where the cover is lost above the tension steel, maybe due to abrasion, maybe due to a little bit of corrosion of that tensile steel, which produces spalling. And how do we select sprayed liner thickness for that case where we've lost the cover? And then finally, what happens if we've got a severe deterioration condition where the tensile steel itself is corroded and we're now providing the liner to restore the structural capacity, the moment capacity, following the loss of that tension steel? So we've developed, or I've developed, a couple of design methods. First of all, with a consultant in Ontario, Ian Doherty. Ian and I developed a design method for corrugated steel structures that's based on the load and resistance factor design framework from the American Association of State Highway and Transportation Officials. So this is a framework which takes account of earth loads and vehicle loads, or live loads, and allows us to ensure that the factored moment resistance, which is the moment that will produce cracking in this sprayed liner, to make sure that exceeds the factored demand, the expected vehicle load, or moment due to vehicle load and moment due to earth load. And so this equation is this load and resistance factor design framework, and details of that are presented in this paper down here. That particular design method allows us to take account of the stiffness of the repaired system based on what's called moment arching factor. And moment arching factor tells us how the demand, the expected moment acting on that sprayed host pipe, is a function of the stiffness of that repaired system, the flexural rigidity, EI, around the circumference, as a function of the modulus of the soil and the diameter of that repaired system, just based on this simple equation. It's in these two publications that I've shown here at the bottom. We were able to do some experiments that were funded by the 407 Express Toll route across the Greater Toronto area, published in this particular paper in the Transportation Research Board, where we had two corrugated steel pipelines of 1.2 metre diameter that were sprayed, one of them with a 2-inch liner, one of them with a 3-inch liner, and we're able to measure the strength. During those experiments, we were able to take measurements of strain, circumferential strain, at the valley and the crest of the corrugation at these two locations over here, and also on the inside of the liner. And then we're able to plot through the thickness of that section, or through the depth of the section in this vertical direction here across that section, and how does strain, circumferential strain, vary through the thickness. So strain measurements at the crest and the valley of the steel and on the inside of the liner. And what we found is that at the invert, where we've got corrosion, we get a very good bond forming between the sprayed liner and the deteriorated steel, and we get full composite action because we've got these linear distributions of strain. But in other locations where we've still got zinc present, we may not get that composite action. So it allows us, we've learnt about where we can assume composite behaviour and where perhaps we need to consider different sorts of behaviour. There's a paper in a more recent conference from the ASCE where I've outlined a composite theory and the equations for a composite theory. And that composite theory considers what sort of vehicle load for a culvert, what would be the capacities to support vehicle load as a function of the liner thickness and as a function of the interaction between the liner and the existing host pipe. Is there composite behaviour between those two, or do we just design assuming that liner is providing all the resistance? Also, do we design based on the full rigid pipe moment, or do we account for the fact that the deteriorated pipe system is not rigid, it's semi-rigid, and the moment is reduced? And here's a couple of measurements of moment capacity measured from the experiments versus calculation of moment capacity based on these different design models. Finally, I wanted to just touch on the behaviour or the design methods that we've published for reinforced concrete, for sprays in reinforced concrete. These conditions that I mentioned earlier in my presentation for where we've got an intact system. So we've still got our tensile steel, we've got our compressive steel, we've got still cover over the tensile steel and the liner sitting under that, and the moment capacity of this combined section where we've got just spraying of the liner to repair the leaks. What happens if we've got the typical service condition where the concrete will crack through the concrete, past the tension steel, and design considering that condition. Design condition considering what happens when the cover concrete is gone due to spalling or abrasion, and so this condition here. And then finally, if we've got loss of the tensile steel because of corrosion and we've got full crack condition, or even the situation where the pipe is, the capacity of the pipe, the existing host pipe is, we're concerned about that capacity and we want to just design considering the capacity of the liner alone. These design equations are all presented in this paper that was published last year in Tunnelling and Underground Space Technology. And I'll just show you one particular case. This is the situation where we've got an intact pipe. And I thought I'd just present this condition because it's a little bit unusual in that actually we have to think of two conditions. One, where we've got, so here's the strain through the profile on the vertical axis, and here on the horizontal axis, we've got the distance through the composite section. So that distance through the composite section would be on the vertical axis here, and it's being presented on this horizontal axis here. So it's showing from the theory, this linear theory that we've developed and published with the design equations, is this linear dashed line here. This curved line is what you would calculate if you did finite element analysis, which allows us to have a more exact solution, but based on numerical calculation rather than an equation that you can put into a spreadsheet. And here we've looked at two conditions, one where we've got cracking of the concrete and one where we've got cracking of the liner. In this instance, what we're recommending for the intact case, we design against cracking of the concrete. And the reason for that is that we believe that if the concrete cracks, the liner will then crack because there'll be a stress concentration on the outside surface or the inside surface of the pipe where the liner is bonded to that host pipe. And we need to prevent that. Well, we need to consider the possibility of a crack developing in the intact concrete and then causing the liner to crack. And the other conditions are discussed in the publication. Here, I've got a little presentation or a summary of how liner thickness, sprayed liner thickness, produces different levels of moment capacity. In this instance, for 3 pipe classes, so this is how we classify pipe strength, reinforced concrete pipe strength in North America, class 3, which is a common pipe that we use. And then as we go deeper into the ground or shallower under vehicle load, we will use higher strength pipes like class 4 or class 5. And here we show what is the required liner thickness based on the design calculations for these different classes of pipe producing these different levels of moment, applied moment for different conditions. So we've got the cracked condition, the cover loss condition, and the condition where we've got steel loss. And it shows how we have to have greater liner thickness based on further deterioration of that reinforced concrete host pipe. One set of calculations for one particular diameter of reinforced concrete pipe. And we can also relate that to burial depth. Let's say we're just concerned about earth load moment. One of the jurisdictions, or in fact the jurisdiction that prompted the development of this work, is the City of Toronto. The City of Toronto believe that their structures need to be designed for the full moment earth load moment demand. It's debatable whether that full earth load moment will ever act on the liner, but they're concerned that somewhere during the service life of that repaired system, that full earth load moment will act. And this shows what you would calculate, the design model would say would be the required liner thickness for different burial depths based on designing for that full earth load. Finally, I wanted to just briefly mention that there's some recent test data, actually from a PhD in the University of Sydney in Australia, where they looked at bond, and they tested the effectiveness of bond between reinforced concrete and different sorts of mortars and geopolymer sprays. And what they found is that within about 3 years, different geopolymer mortars, which are some of these commercial products or many of the commercial products available in the industry, are these geopolymers, and they've been seeing that there's been a significant loss of bond between that geopolymer mortar and the host pipe, whereas the conventional cement materials tend to keep their bond much longer. The data is only available for about 2.5 to 3 years. And so this data prompted us to look at that assumption of bond between the sprayed liner and the reinforced concrete structure. And what we find is that if you have zero bond, an assumption of zero bond for your design calculations, at very small thickness of liner, the liner will adopt the same curvature as the host pipe, and the liner will do very little to restrain that curvature. So it adds very little to the stiffness of the system, and so it just goes along for the ride. And as you increase the liner thickness, the distance from the neutral axis of the liner to the extreme fibre increases, and so the tensile strain will increase. So initially, as we increase the thickness of the liner, we get more and more tensile strain. Eventually, as that liner thickness increases, it provides stiffness to the composite system. And so the curvature that is going to be developing starts to mitigate. So the maximum strain in this liner that's not bonded to the host pipe will go through a peak and then decrease. And for some of these sprayed geopolymer sprays, there'll be a zone where we have unsafe design, where the actual strain demand will exceed the rupture strain of these sprayed materials. And since we're recommending that the design of these sprays be to prevent cracking of the spray, this zone would be a range of thicknesses that would be unacceptable for those sorts of products. And so we need to then think about when might we have that unsafe thickness range, and there'll be certain circumstances where we can design down in here, where the liner will produce strains that are safe, but otherwise we might have to have very thick liners to produce behaviour. So let's say we had bonded design down here for the cracked condition for different levels of class. So here's our thickness versus the burial depth. Then we'll have a zone in each case where the unbonded design would produce unsafe design. And so there'll be a range of liner thicknesses. Let's say at 5 metres, we might be able to choose a liner thickness that's in this range, between 20 and 60 millimetres, where we'll have safe design. But at one of these deeper covers, we might have a range where we have to have a thickness that's greater than the bonded design, but is actually then into this unsafe zone. So we have to choose much higher thicknesses so that it satisfies the design constraints for both bonded and then after a few years, potentially unbonded design. And so we might need to have a much higher thickness for those conditions. So I'd just like to acknowledge support for this work from the Granting Council, NSERC in Canada, some of the research partners, some of the people who've helped me do the work, and thank you again for the opportunity to make this presentation. And finally, if you're interested in any of this work, please feel free to contact me by email. You'll find my email address at the Queen's University, or just Google Ian Moore, Queen's University, Canada. You'll get my email address, and I'd be very happy to supply these publications if they're of value to you. Thank you very much.
Great, thank you very much, Ian. That was a fascinating discussion on both the CIPP and the sprayed liner. If anyone wants to ask questions, if you'd like to type them in the chat. In the meantime, I can ask you a couple of things, Ian.
Sure.
It was very interesting to hear what you were saying about the cured in place liners, because I think that's being used so much with, you know, projects like HS2 over here.
Yes.
And other sort of projects of that type. And in fact, I was involved in the City of Toronto LRT project, where we were looking at all the movement of various infrastructure under the mined stations.
Yes.
And it just made me think about, perhaps you could speak a little bit about the differences of looking at pipelines that cross perpendicular to a tunneled section compared with pipelines that are kind of running parallel, and particularly how it pertains to those slippage lengths that you were speaking about. If you have anything to add to that.
Yes. Okay. So so that's like the Eglinton station and so on you were involved with, Sandra?
It was a number of them. It was sort of Laird and Leaside.
Okay. Wow.
Oakwood,
that's great.
I can't remember. There was 4 in total.
Yes. Okay. So what I've been presenting this afternoon allows you, if you know what the kinematics, what the motion at those joints, at those ring fractures are going to be, you can now make an estimate of what the local stress and strain will be in the liner. There's a separate calculation, and I assume that in those projects you're doing, Sandra, you're probably having ground motion analysts,
Yes. Yeah.
modeling, doing three-dimensional finite element analysis of those mined stations. Those three-dimensional analyses will typically produce patterns of ground motion. Perhaps we typically think of like tunneling induced ground motion as being some sort of normal distribution, and we have sort of empirical measures of how much vertical motion we will get, how far out from the tunnel it forms. For these more complicated geometries associated with mined stations, there'll be much more complex patterns of ground motion.
Yeah.
And typically those analysts produce the free field ground motion. Okay,
Yes.
they don't tell you what the pipe is going to do. They say this is what the ground is going to do. So then there are techniques, and there's some other publications if people are interested, and I haven't talked about that today, where you can go from the free field ground motion to estimates of how much rotation and axial extension you'll get at specific joints. And it's typically we sort of clump all of, let's say, the rotation that we might expect along a certain segment of pipe, let's say halfway along one barrel, past a joint to halfway along that next barrel, and we'll clump all of that rotation and we'll clump all of that axial extension at that joint. But you're absolutely right. Depending on whether the tunneling process is parallel to those pipes or transverse to those pipes, typically if it's transverse, we'll get shorter wavelength motion. Shorter wavelength motion will produce higher rotations and higher axial extensions. Whereas if we're tunneling parallel to those pipes, depending on how that tunneling progresses, is it like the tunnel face is sort of advancing like a wave and producing a ground motion like a wave? So that might produce a fairly severe demand on those joints. But if we're tunneling so that we're excavating the whole of that section and then we're slowly going down it with depth, we'll tend to produce a much longer wavelength behavior and significantly less demand at the joints. So it's a little, I'm trying to describe it with words. Of course, I don't have a picture to show you, but hopefully I'm making sense. And definitely whether you're tunneling parallel to or transverse to, and whether you're excavating the whole tunnel and advancing it along the line of the tunnel, or you're creating you're excavating the top half of the tunnel and slowly excavating down, that will influence how much demand you get on those joints and potentially new fractures. So Thanks for your question, Sandra.
Yeah, no, thank you for that. So we have a question from John Gumble.
Hi, John.
And he says, great results for design of CIPP liners to resist joint opening displacements in the hose pipe, but do you have any plans to extend the analysis to consider the impact of an initial annular gap between the liner and the host, as typically occurs at least in non-pressure sewer applications?
Very good. Thanks, John. Okay, so different, and John is a CIPP guru and understands a lot about CIPP liners, but I'm not necessarily saying this for John's benefit because I've learned a lot of this stuff actually from John. So if you have heat cured, let's say felt liners, they do tend to experience shrinkage during curing. You will get a gap. And the work that I've done to date is based on the conservative condition that there's zero gap. That might be a reasonable approximation if you've got a light cured, sort of ultraviolet or different wavelength of light cured or photon cured, typically fiberglass CIPP liner system. They tend to have much less gap, or some of those products, it depends on the product, has less gap. And so this work that I've done to date is that conservative condition, or it will be conservative if you've got situations of initial gap. But that's a really good point, John. And subsequent students, in fact, I'm hiring students at the moment. We'll be looking at these other conditions where we've got an initial gap between the two. And I think in many circumstances, the initial gap will completely protect the liner from any sort of, or will largely protect the liner from distress. But that's just a kind of judgment. And we need to do the calculations to establish that. But yes, that's the next point of that program of research. Thanks, John.
Excellent. And we have a question from Martin Long, who asks, was the potential bonding due to mechanical interlock at pipe joints when CIPP is inflated and cured considered as part of the assessment of friction bond between the liner and the hose pipe, or is this not a concern?
What a great question. I love that question. The assumption that this work that we've done to date is that the slip between the liner and the hose pipe does not propagate past the next set of joints. So if we're looking at a specific joint, there can be extrusion of some of that resin, depending on the liner system, less likely for, say, a fiberglass liner, more likely for a resin impregnated felt liner. That extrusion will produce a little annular sort of bead of material, which you're absolutely right, will tend to lock in at those subsequent joints. And the research that we've done to date assumes that the friction or the slip that we get between the liner and the hose pipe does not go past one of those locked-in conditions. If it does, then the solution we've got will not be conservative. So if you had slip, let's say for a gravity flow liner that went beyond those points where you'll get that locking in actually of the motion, the solutions that we've presented to date will not be conservative. So it's like a lot of these things in research, we take steps forward, and that's as far as we've got. So I really appreciate your question, mate, because we need to be careful understanding that as we apply the design equation that I've presented today. Thank you.
Great, thank you. And thank you for the great questions. I don't see any further questions. So, and I don't see anyone typing. So
Very good.
Thank you, Ian, for
You're
a
welcome.
really fascinating presentation. And I'd just like to thank everyone for attending today. And just to let you know that you can find other events from the Pipeline Industries Guild on the Pipeline Industries Guild website. So thank you all very much. And thank you, Ian, for a fascinating presentation.
Thanks, Sandra. Thanks, everybody. Have a good afternoon.
Thanks.